single carbon-carbon bond. But what happens when we try to rotate around the double bond? We can't, can we? And the same thing actually occurs in the actual molecule itself. So the bonding's a little bit different. We don't have 4 sp3 hybrid orbitals. Let's draw the formula first of all for ethane. So I'll rub out our methane. Let's go up to ethane. We have 2 less hydrogens. And so we're going to find we're going to need 2 less of these sp3 orbitals. So let's just remove these middle ones. And well, I haven't done over here, but I'll quickly draw this in. The electrons in. Okay, now every carbon now only has 6 electrons. We need to put the other 2 somewhere. Now we've only created here 3 sp3 bonds or orbitals. So let's get rid of one. Of course, where is the other one going to be? We've already used up the S. We've used up 2 P's to make that. So S plus 2 P's gives us 3. We have, in fact, 1 more P orbital left over. And of course, remember, it's going to be higher in energy. So now there's a single P orbital left over. Now, remember P orbitals are dumbbell shaped. And so what happens is the P orbital is here, and it's 90 degrees to the sigma bond. And there's an interaction between these orbitals. You put an electron here, put an electron here, doesn't matter where we put them. But what we find is it forms a new type of interaction or bond called a pi bond. Okay, and so now we see we have a bond between the 2 carbons which doesn't stop rotation. But if I try to rotate around now, I've got this interaction which I'd have to break, and hence the double bond doesn't have free rotation. Now the implication for this is, say for example, let's increase the chain. Let's do but2ene. So I'm going to change this hydrogen to a CH3, and let's change this one to a CH3. We can see that these 2 CH3 or methyl groups are across the double bond. We can also draw this with them on the same side of the double bond. And the 2 are not equal to each other because I can't freely rotate around this bond to change one into the other. In fact, these are what we call geometrical isomers, or the cis isomer, cis being the same side, or Z same side, it's actually German, and trans meaning across, and the German for that starts with E, note that it's an E isomer. And in fact, when naming these, because they are different compounds, they're actually going to have different reactivity, believe it or not, and some different physical properties. We can't call them both 2-butene or but2ene. We have to call it E-but2ene, E for trans. And we're going to have to call this Z-but2ene, or cis-butene. Okay, so this is another thing predicted by this hybridization model. The last thing I'll get you to consider is let's go from alkenes. What's the other homologous series that we've studied? The alkynes. So, getting a bit messy, let's start again. Okay, make a bit of room. So, let's draw the simplest alkyne, which is ethyne, or acetylene. This is acetylene gas used in MIG welders and things like that. Okay, let's start off. We have a sigma bond, okay? That's one part of a triple bond, one part of a double bond. Always start with that. So let's overlap our sp3 hybrid orbitals to form our sigma bond. Okay, we've only got one hydrogen, so we have to use up another sigma bond for each of these. The s orbital of the hydrogen. Put the electrons in. And how many electrons does each carbon have around it? Only 2, 4. It needs another 4 each. So we've already seen one trick, or one way this can happen. We have our p orbitals 90 degrees to that bond. Okay, we can put electron in each. It has that interaction. They're effectively sharing those now. Each carbon now has 6 around it. Of course, there's another p orbital left, isn't there? So far, let's count the orbitals. 1 sp3, 2 sp3s. So, we've only made, in this case, we have that extra p orbital left, don't we? Okay, and of course, we'll get another interaction, but this time in and out of the board. This is like a propeller, if you will, if you're looking down the compound. And of course, we can put our electrons in. Doesn't matter where I put them. And now each carbon has the required 8 electrons around it. It is now stable. Each one of these carbons is now an sp hybridized carbon. Okay? We've used one s, one p to get 2 orbitals. Remember the alkanes. So this is sp hybridized. An alkane we now call sp2 hybridized, and an alkane we call sp3 hybridized. Okay, again, an alkyne triple bond also has no free rotation about it. So here's a model of acetylene or ethene. We can see definitely can't rotate about those 2 carbons. But what do I also notice in this molecule? We've got a lot of electrons between those 2 carbons. That's a very high energy situation. In fact, what we find is the reactivity of a triple bond is far greater than that of a double carbon-carbon bond, which again is greater of a single carbon-carbon bond. And what we find is the reactivity of alkanes is very low, alkenes is much higher, and alkynes is higher again still, which is all predicted by this model. The reason this has a linear shape, by the way, is because to minimise the impact of these 2 electrons, 180 degrees really represents the angle to get them furthest away from each other. All right, so that's all I wanted to show you today. Again, you know, carbon can form all these different types of compounds because you can have isomers where we can, say for example here, let's make this into butane. Okay, we have butane, and then if we just rearrange the bonding, let's move this N-methyl group, put it onto the second carbon of the now 3-membered chain. We start off with butane. What's the name of the compound we've ended up with? I'll let you have a go at trying to name that. So just press pause and try and name. Unpause. Longest chain is 3, so it's a propane. And we have an alkyl group, a methyl group on the second carbon, 2-methyl propane. Has the same formula as butane, but it's a structural isomer. Of course, the longer the chain gets, as you can appreciate, the more and more structural isomers we can have. Remember, free rotation, we don't count every different configuration by rotating as a separable isomer. It's actually called a conformal isomer, but basically they have the same chemistry. Of course, we can also have alkenes. They can be branched as well, just like alkanes. So there's lots of different structural isomers. But as well, because of the lack of rotation about the double-double bond, if I break this bond, break that bond, so I'm not rotating, I'm breaking bonds, making a new substance, this has, you know, it's still a methyl group on each carbon, okay, but they're on different sides of the molecules now. This is a geometric isomer. This is trans-butene. When they're on the same size, we call that cis-butene, geometrical isomers. So you can imagine, again, that increases the number of different compounds that carbon can make. Carbon has a very stable carbon-carbon bond. It can form these alkyl chains up to 10,000 units long. In fact, that's what we'll find most plastics are made of, for example. No other element can do that. There are elements like sulfur, for example, that can have double, single, and things like nitrogen can have triple bonds. But the strength of those bonds are not as strong as the carbon-carbon bond. Those molecules aren't as stable. Carbon forms more compounds than anything else in the periodic table. Well, I hope you've enjoyed today's clip, and I'll see you soon. Carbon out.